And also, I'm very happy to be here, and also thank you for the fellowship, which I really appreciate. It gives me a lot of free time, and also have wonderful discussions, including the self in monkeys and other interesting things. So thank you very much. And I hope maybe the first part of my title is probably clear to you. I hope you're all by full consciousness now. The second part might be a little bit mysterious for you. What on earth do I mean by dynamics, topography, and common currency? I will not explain this now. I will, throughout the talk, I hope you get an understanding and why that is important. First, of course, you know there's a huge debate about consciousness. In March, there were pseudoscience, the integrated information series called pseudoscience by IIT concerned people. So there's a big debate, different theories of consciousness. And you probably ask, why on earth, Northoff, do you need to add yet another one? So I don't go into some of that. We can leave that for the discussion. But I just want to say what I mean by consciousness is subjective experience. So what it is like. It's not you perceive me, you see me, your visual cortex becomes active. You know this more, the two of you know this much better than I do. But there's a certain way I experience that visual content. So that's very important. So something in addition comes with the content, and that's the experience, what it is like. Let's say, for instance, I can see your face, but I cannot feel and experience and see your boredom when you say, oh God, Northoff gives another talk. I'm not listening, I'm bored. Yeah? So that's very important, and I was already saying that. So it's really the what it is like, consciousness. That's what I try to explain here. So, and I already said there's something in addition. So, and the approach I take here, I don't want to get into much of the conceptual issues, but one thing we really need to point out. The current theories of consciousness, almost all of them, except the predictive processing, always adds a special feature to the brain. So they say, okay, consciousness is a special feature which comes on top of all the other non-special feature. So be it integrated information, Tononi, IIT, posterior regions, they have a special grid, or the global neuronal workspace say, okay, you need to trigger dorsolateral prefrontal cortex, ignites the global workspace, recurrent processing, higher order. So something, there's a non-special processing in the brain, and on top, there is an add-on special processing, special feature. And that conceptually, and this is very important, in the philosophical tradition of the Western world, that can ultimately be traced to Descartes. Yeah? It's a neuronal dualism in the brain. And of course, the proponents of the series would kill me for that. And we chose another approach. So we say, okay, of course, consciousness, experience of content through what it is like, but the most non-special features of the brain. So that's where we try to go in and say, maybe these non-special features, and that's space and time, and that more specific topographies and specific forms of dynamics. So, and I said, I will, throughout the talk, I will explicate these features. So that's a conceptual background, which is really different. It's also in the Western tradition to escape a potential dualism. Because once you're in that space of possible dualism, you're trapped. Your philosophical tradition, as far as I understand it, is different. You do not have this strict distinction, but I'm not an expert. So, and now in the key feature, conceptual feature, that I say, look, there are shared spatial temporal features in your brain and in your subjective experience. So I take subjective experience extremely serious. Yeah. So I listen, for instance, in the psychiatric patient, I really listen to how they experience their anxiety, how they experience their hallucination. Because the psychiatric patients do not come to me because of their hallucination. They come to me because of the meaning they attribute to the hallucination. And I'm after this meaning, this subjective, experiential, what it is like component. So, and I decompose that also on the phenomenological level in terms of time and space. So I look, for instance, for inner time and space experiences in psychotic patients, in other forms of interesting mental states. You will see this in my talk. And for instance, we also investigate now meditative states, and again, phenomenologically invective. So I say that basically there's a shared feature between the spatial organization and the temporal organization of the brain's activity with the spatial and temporal organization of your consciousness. And that leads, so I show you here the consciousness, that leads to a whole new line also of psychiatric research, which I haven't shown here. I will touch upon a little bit of that, but you can read it on my website. So that's the conceptual background. And now I want to basically explicate some of that. Yeah. So the first, I will talk about the space of the brain. I show you some results, Owen and others, on topography. Then I go into the dynamics. Then I go, in particular, one component is the phase dynamics, shaping of specific contents. And you see it becomes specific features of consciousness, yeah? Inner, outer, the balance of inner, outer contents, conscious contents, the specifics, the contents of consciousness, the specific contents. And then at the end, I basically wrap it up, the last part, temporal spatial theory of consciousness. As I said, I will try to keep that short just to wrap things up. And I will also, at the end, I will show you some practical implications for interventions in mental health. So I think it's very important. Every theory of consciousness is only valid if it had direct practical application. Yeah? Let's say if your car works and drives, the engineer must have done something right. So that's the way I consider it. If therapeutic intervention works on the basis of my temporal spatial principles, then you can argue conceptually with me, but I must have at least something, at least 1% right. So that's why I show you that at the end. So let me start with the topography. So when I bring here the example of meditation. So I got into meditation through some students, and now we have actually a very intense collaboration with India and Bangalore. We have lab meetings every week, and they really introduced me into the world of meditation. And two key concepts of meditation are mentioned here is equanimity, that basically you detach, you de-identify yourself from specific content. So usually, let's say you have a certain affective content, you feel a slight anxiety, and you identify yourself with that anxiety, and of course the anxiety becomes stronger. Same with certain thoughts, but in meditation you try to de-identify. And the key concept here is the non-duality. Some of you probably may know this. It's basically you don't make a distinction anymore between your inner self and the outer environment. It's no longer a clear-cut distinction as we usually experience this dichotomy, but when you, particularly advanced meditators, they really do not experience a difference. And the Indians, there's a long tradition in India. When you go to India and you start talking about non-duality, you get at least 50 opinions from 20 people. It's unbelievable. So this is for them an absolute key concept, and it's really interesting. It has philosophical, metaphysical, empirical, phenomenological connotations in India. So it's probably a little bit like your concept of the chi as fundamental in the Indian metaphysics. And of course, so now, but we try to tackle that on the psychological level. So how can we investigate it? So here's, I tell you, for instance, here, it's really here, that's a traditional C. Here you see we have a self-other distinction. This is clear. I can distinguish myself from you in the experience and our beliefs, and that really results in the corresponding thing. However, the proficient meditator, many, many hours, often many, many years, they don't make this distinction anymore. Yeah. So it's really, there's a whole, as I said, there's a whole philosophy, a phenomenology also to it, which has a long tradition in India. And they call this non-dual awareness. There's somebody in New York, Josipovic, who has beautiful description of the non-dual awareness, but I spare you the details. So then the question is, how can we investigate it? So here we did, and you can see here on the lower right, I think this is from the first author, Austin Cooper, a very nice figure here. you see there's a duality in the non-proficient stage, and in the proficient stage, you experience yourself as completely as part of the world. You don't make a difference anymore. And often, So the question, how can you investigate that? So we did a meta-analysis, a large-scale meta-analysis of fMRI studies in meditation, different forms of meditation, because we said the most important thing is the non-dual state, and we investigated that in proficient meditators. And so, one particular focus was on the relationship between the default mode network and the control executive network. So these were functional fMRI studies, usually in the meditative state, and usually it was investigated various forms of functional connectivity. And you can see what is typical. You see in the ones of you who work in fMRI, you know it's usually a negative relationship, a reciprocal antagonism between the default mode network and the control executive network. So meaning if this, the DMN shows high activity, the control executive network shows low activity, and vice versa. It's quite a well replicated finding in the imaging literature. And exactly that antagonism, that duality between the two networks is no longer there in the proficient meditators. And how is that you have a lot of high degrees of functional connectivity between the two networks? Yeah. And what is functional connectivity when you go back physiologically? Yes, it's the time series correlation, but physiologically, it's ultimately based on the coherence of the phase, ongoing phase fluctuations between the networks or between the regions. So it's ultimately a phase-based synchronization of the network. And if the two networks are highly synchronized with each other, you do not make a difference anymore in the experience of their contents, meaning you put them together. So, and what was interesting, then this is a schematic figure, what we observed. I focus your attention on this one. So this was the negative relationship in the novice, in the non-proficient meditator. These were sort of meditators in the intermediate stage. So you somewhat see they balance in the opposite extreme, and then you don't have any. This is the highest level of synchronization and the highest level of functional connectivity with it. So you can see the details in the tables of that paper, and you can really see it's an increasing synchronization. And we have, just last night, we reviewed other data of ours where we really show the whole brain is much more synchronized with each other in the proficient meditators. So then we also investigate, in addition that, because it's about self and non-self. So, and you may remember, I think 1.5 years ago, I gave a talk about the self, and we have this sort of 3-layer topography of self, where you have regions related to the interoceptive self, to the exoceptive self, so the outer body self, the inner bodily self, and the mental self. So this is an established set of regions which we worked on in various studies and a large-scale meta-analysis, and we looked how that is how these regions are activated and show functional connectivity in the proficient meditators. And what you can see, so usually in the non-meditators, you have a lot of activity in the regions of the mental self. That is usually cortical midline structures, default mode network. Less activity in the exoceptive self processes. There's a lot of temporoparietal junction, premotor cortex, proprioceptive, exoceptive integration. And then you have the interoceptive region, which is the insular thalamus salience network region, which is typically interoceptive processing. So basically these really dominate. However, in our meditators, in the proficient meditators, we found the opposite. Yeah, that now the functional connectivity and activity in the interoceptive processing regions was much stronger and much less in the mental self. Now, phenomenologically, sorry, I'm going back. So phenomenologically, what that is, that you usually hear, you have all these thoughts coming, you have mind wandering, yeah, and however, that's exactly no longer there in these proficient meditators. So you really have a shift, And the interceptive region is not just interceptive region, it's intro-extroceptive coupling. Yeah, that's, for instance, the insula integrates these two types of inputs. So you really see, that's what I would say. The point I want to make is the topographic reorganization in these meditators. And that shapes their experience from dual to non-dual. Of course, now you say, and you were absolutely right, Northoff, please show me a direct relationship between this topographic reorganization and the experience of non-duality. We're working on it. Yeah, so that's exactly. But now I show you some other findings, which I will not go much into. Is, for instance, I showed you that basically the DMN and the control executive network are no longer are flat. It's completely no distinction anymore. For instance, in depression, it's the opposite. In depression, you have extreme focus on the DMN, abnormally high activity of the DMN. This is a paper from 2020 and another one this year, where we could really show that in depression, you have exactly the kind of pattern. You have extremely abnormally high activity in the default mode network. Everything is shifted towards that and less in the unimodal regions, the sensory regions. So what do you see phenomenologically in depression? You see extreme rumination, the exact opposite of the meditative state. Yeah? So, and here in meditation, you have an abnormal focus on the mental self. Yeah? You crease, everything is wrong, I'm guilty, I cannot be. Everything is focused on the self. So you have a complete shift from the focus on the environment to the focus on the self in your mental phenomenology. So I spare you that one. So that's what I'm trying to describe here. Content shift towards the inner self, increased self-focus, and decreased environment focus. That on the side that goes along together with an abnormal slowness, but I will not get into that now. So here, this is a very recent paper. When we put things together, we were asked to write about the default mode network, and we tried to link it to inner time consciousness and this experience. So here I show you, maybe you start looking here. So basically, you have a whole continuum of different configurations of, let's say, default mode network and sensimotor networks, meaning transmodal, unimodal balances. And what you can see, if everything is focused towards the DMN-centric topography is abnormally high, that's when you see depression. Now, you see opposite as a psychiatrist, when you have the topography shift towards the sensimotor network, that's what you see in bipolar mania. And suddenly you're completely focused on the environment. Yeah, you're no longer focused on the self, but you focus on the environment. By the way, these beautiful figures I owe to Bianca Ventura, who is a master student of mine from Italy. She's incredible. So, and in the balanced state, which you see in meditation and psychedelics, in psychedelics similar findings are reported, you really see a balance between DMN and unimodal regions. Yeah, so usually you have a balanced transmodal, unimodal, but now it's completely flat, and you don't make an experiential distinction anymore between self and other. So that becomes blurred, and that's exactly what these people experience. So now we are trying to run study to make a direct link between these phenomenological features and the neuronal features, and this is a review of various other papers. So the point I want to make here, that your neuronal topography shapes your mental topography. The way you experience space. Yeah, we now run a large-scale 30-center global worldwide study about a time-space questionnaire for mental disorders. So in depression, you experience the space extremely tight. Yeah, a recent patient of mine said, okay, I feel like in a dark tunnel without exit. Yeah, that's the space in depression. The space in mania, it's an open space, I'm lost. That's what they literally tell you. And in meditation, it's clear. It's a balanced space, I'm part of the environment. That's what they experience. So I hope I could make the case that maybe here there's a shared topography. I do not reduce the phenomenological or mental to the neuronal, but I share some underlying similarities. So that's very important. That's really the unique approach of our spatiotemporal model. Where there is space, there's also time. You all know this, they always go together. There is no doubt. So now I will try to show you that the dynamics of the time shapes, or dynamics shapes the content of consciousness. What do I mean by dynamics? Dynamic means basically the pattern of change over time. Very simple. So, and here I start again with meditation. Meditation is a perfect tool because it gives you so interesting mental states. Yeah, it gives you the phenomenological experience where you can really make specific neurophenomenological hypotheses. So here, this is now EEG data. So what we did, we investigated, and that's now Bianca Ventura, the one who does these beautiful figures. We see 3 forms of meditation. So we did mantra, where you have a set of chants. Yeah. Then we did the here vipassana, where you have to scan your different bodily objects. So you scan mentally, let's say this point, you scan your nose, you scan this one, you scan this one, you scan your heart. It's incredible the kind of techniques they developed. It's unbelievable. Yeah. And here, shunya meditation, that's a meditation where you don't focus on anything. So you just let your thought contents and perceptual content pass by. So I always compare this to clouds. So you let the clouds pass by the wind, but you don't identify with any clouds. It's just passing by. And when I ask the Indians whether that is a correct description, they agree. Yeah, so it's passing by, but you don't follow that. So that's the same, you completely detach yourself. And now what you can see, so you see in the Vipassana, now I look at the induction and the temporal structure of the induction. That's very important. The ones who already worked with me know that I usually like to focus on the temporal structure of your experimental paradigms. Same here. Oh, sorry, I need to drink a little bit. So same here. I look, what is the temporal structure? So here, in the Vipassana, you have a very discrete, you focus on one object and then on another. So you have a short attention blocks. So your attention is temporally sparse, passed into different time units. Now in the chants are longer. So you have a slightly longer attention window at the exclusion of others. Now, in the shunya, remember that was the cloud where you don't identify, you just let your thoughts pass by. It's a very long attention window. Yeah? So now we said, okay, look at the temporal structure of the induction method. So longer window, medium windows, very short windows. Now we investigate the temporal windows in the brain's activities. This is EEG, as I said. And so now we look for the temporal windows in the brain, and how can you measure the temporal windows? It's basically the duration of activity. You can measure that with what is called the autocorrelation window presented there. So how you calculate it, I take the degree of correlation in my activity between T1 and T2, T1 and T3, T1 and T4, T2 and T4, and so forth. And then I can see, of course, with increasing temporal distance, increasing temporal legs, here, down here, of course, I have less correlation of my amplitude. And that's what you can see. And then you usually, you can take out the red points where you can measure 50 degree of correlation or 100% or 0% of correlation. So that's the autocorrelation. So the hypothesis was that here you have the longest autocorrelation window in the brain. Here you have the shortest, because that corresponds to the temporal structure of your attention required in the respective tradition. So, and that's exactly what we saw. You see the results down here. So this is real data. So you saw a very short autocorrelation window here when they had to focus on the different bodily parts. You see this here. You saw a slightly longer autocorrelation window when they had to do the mantra, the chanting. And you saw a very long autocorrelation window when they just had the cloud-like meditation. So now we say, okay, look, the time scale duration is similar on the neuronal level and on the psychological level. So of course now next step, what we need to do, and exactly that's what we're doing now, that we're trying now to measure the duration on the psychological level, yeah? Because you want to have similar measures on the neuronal and on the psychological measures. However, that is not always easy because you require a lot of data points and you cannot let the subject continuously judge during the meditation. So here you see again correspondence between the attention duration and the neuronal duration, which admittedly experimentally we need to follow up particularly on the psychological and experiential level. Now you can say, yes, Northoff, you tested for attention, but you didn't really test for consciousness. And of course, we all know that the relationship between attention and consciousness is a complicated one. There's even a attention schema theory by Graziano. So you would need to show, I would need to show, that these temporal windows, or the autocorrelation window, is indeed related to consciousness. So how can you do this? One way is indirect, that you can investigate the autocorrelation windows in disorders of consciousness where you lose consciousness, as for instance in sleep or in coma, vegetative state, unresponsive wakefulness, or in sleep. So I don't show you all those data, but I can tell you that in sleep, we have the longer you sleep, and 1 and 2, the different sleep stages, and 3 and REM sleep, usually your temporal windows become very long. Yeah, your power spectrum gets into the slow frequency range. So here I show you the data from coma, unresponsive wakefulness. This was about 40 patients, and they were either minimal conscious state or unresponsive wakefulness. And you can clearly see here the autocorrelation window becomes much longer when you lose consciousness. That's a replication of earlier finding of ours, and others replicated that in the meantime, that indeed that's probably also related to the increase in the slow frequencies in your unconscious state. So, and you can see this here, we calculated the autocorrelation window in different ways, and you always see the blue ones are the unconscious. You see frontal and occipital electrodes. So it's a whole brain phenomenon. Your brain becomes slower, your temporal windows become abnormally long. That's important. And then we say, maybe that is it really related to the change in the power spectrum? As you may know, when you become more and more unconscious, you lose your alpha peak. When you see a pure, complete unconscious N3 sleep, or in coma or in anesthesia, you really see that alpha peak disappears. And that's exactly what we observed also in this sample. And interestingly, so it's a very fine grain, it's the first author, Spinoza from Italy. He did a very nice, he's not related to the philosopher Spinoza. We always made that joke when he was there. And you really see that the people lose their alpha peak, yeah? And interestingly, in some patients, it shifted to the theta range, and then later in the more advanced stage, it's disappeared. So now the question is, are the changes, this abnormal, let me see whether it works here. Okay, whether the abnormal prolongation of these time windows relate to the power spectrum, and that's what I show you here. So you can see here is a mediation model. I spare you the details. I refer you to the paper for that. So you can really see that the power, the shift in the alpha peak predicts the level of consciousness. This is measured here with the consciousness recovery scale, CISR, but it's mediated by the autocorrelation window. So that really suggests, and we did this here for the power ratio, alpha versus the rest, alpha alone, and you can see this in both cases. And then here he did it's basically a three-dimensional graph. Here you can see the power, here you can see the ACW, the autocorrelation window, and here you see the level of consciousness. And you can really see the higher, the longer your autocorrelation window, the less your alpha power, and the less consciousness, lower scores means no consciousness, have. So that really suggests, in addition to the other findings, that this autocorrelation window, this temporal windows of your brain activity, is really important for consciousness. So, and you see on our website, we have a whole variety of different studies showing that. So now, what does this mean? So this is a schematic, but based on real data from this 2021 paper. So, and this is Federico Ciglio. He did this again. He's now back in Italy, and he did this wonderful graph. So, what does this mean? So, let me just to make this more clear. So, look at this. So here, unfortunately, this room has only one window size. But if you have different window sizes, you see the same environmental context, let's say the trees and the houses, in different facets. So it's like zoom in, zoom out. You see the details of the branches, the leaves, in a very small window. If you have a larger window, you see, these are the different branches. This might be a tree. And then in a very large window, you see the tree and the house in the back. So what I want to make here, we see the same objects through different window sizes. The same in distinct ways. And that's exactly probably also how the brain works, that the brain has different time scales, different temporal windows, and they give us different information. So now, now I go back to this one, follow here. So now imagine you have a scene. Here, a policeman following the thief. Yeah, you have to have different time scales. The policeman, police, stop, stop, stop. Now, so you need a time scale for each of the words. You need a time scale also for the combination of the words. Yeah, intrinsic neural time scales. Yeah, that is indicated here. And you need very long time scale to link the two. Now, if you hadn't this very long time scale, you wouldn't link these two. You could not connect them. So there's indeed support for that. Now, when your time scales become longer, like I forgot that one. Okay, good. When your time scales become longer, which you can see here, that's indeed data-driven, and one sleep and you're drowsy, you probably perceive things a little blurred, yeah, because you don't have the shorter time scales anymore. Yeah, you lose your shorter time scales, so your temporal resolution is not as fine-grained anymore. We have a whole line of research on the visual cortex with MT+, and we use the motion suppression task, and we use this in depression, and we can see, indeed, we can really show in depression, depressed people are too slow in their perception, and we can literally see that they perceive things less clear. So, and here, when your time scales become even longer, like in N2 sleep, then you see even more blurry, you see less differentiation, and then you're completely unconscious, like in anesthesia. Probably that's what I imagine. So now you can imagine what we're trying to do. Of course, this one, when the people are unconscious, you cannot test them, you cannot ask them. But that's what we're trying to do. So meaning your time scales really shape your perception / your consciousness, the structure of your consciousness. So, and there's various lines of support for that. So now you say, okay, what do these long temporal windows do? You want to know then how is that possible? So one key model and hypothesis in our group is that these long temporal windows, this intrinsic neural timescale, serves the temporal integration of inputs. Yeah, so you have different inputs. When you perceive me, now you see me, I do these movements, and then I do these movements, and you need to somehow integrate these inputs, because you put together in your perception this one and this one. And I would argue you need a temporal window for that. So how can you show this temporal integration? We haven't tackled that in the empirical data, but here I show you a computational model. So this is a computational model based on Chowdhury et al. 2015 neuron. It's the one group. It's a biophysically realistic monkey-driven based model. It's based on monkey data with DTI matrices and everything. So, and the main assumption was that we said, okay, we look whether the temporal duration of your neuronal activity reflects the temporal duration of your input. So here we presented a short input, and then basically this is the computational model data, real simulation data now, that you really showed, okay, in V1, probably no surprise to you as experts, that you really see a temporal representation of the duration of the input. You see it's a clear distinction between the input. However, when you go towards transmodal regions, particularly here 24C anterior cingulate, you see a lot of temporal smoothing. So suddenly your brain does not represent the temporal structure of your input stochastics, but it basically presents a temporal smoothing. So then we say, okay, maybe can we see the same for longer input? And that's exactly what we see. Here in V1, you have a nice representation. In 24C, there's this temporal smoothing. So, and then we measured also the autocorrelation window in these regions. No surprise, it's much longer in this region, it's much shorter in V1. So, and there's a whole literature on a unimodal, transmodal gradient of your timescales. Unimodal regions, sensory and motor, shorter timescales, transmodal, higher order regions, longer timescale. So there's a hierarchy. So now our question was, is this hierarchy important for the temporal integration of the input? So in the Chowdhury model, here the second author on this last paper, Yazir Katal, he found out that there's a little hierarchy index in the model. So what he played with the hierarchy index of this model. So what he did is, so this is hierarchy index performed. So you give for each region, there's a little H classifier, and you give a hierarchy index, and you see the same results as we saw here. In the higher order regions, you see a temporal smoothing of the signal. And that holds for continuous inputs as well as discontinuous inputs. You see even larger temporal smoothing in the discontinuous input. So now he said, okay, I put this hierarchy index to 0. So I don't assign any hierarchical role to the regions anymore. And you see the temporal smoothing is gone. So that suggests, so tentatively, that your hierarchy, the unimodal transmodal gradient, is really important in the temporal integration and segregation of inputs through the temporal windows / the autocorrelation windows, the brain's intrinsic neural timescales. So next question. So then you say, Northoff, why on earth are these timescales so important? Why? Because there's a high likelihood that really the timescales are important to track and follow the environmental input contingencies and stochastics. So on the left, you see a schematic figure here. Let's say you have a robot. That's the real scenario in humans. You have unimodal, transmodal. Unimodal regions have shorter timescales. Transmodal have longer timescales. So that's really relatively well established. So, but now imagine, if you're losing your faster timescale, you're losing your slower timescales. You have only the faster ones. Then you will always dance too fast to the music. And that's exactly the case what you see in manic patients. They're too fast. Their brain activity, of course, is not as extreme as here, but they're literally too fast. And that's what they also tell you. Now, if you have only the slower, but not the faster timescales, the shorter timescales, you're always too slow. Yeah, because you cannot follow the faster environmental contingencies. That's the situation in depression. So you need a multitude of timescales in order to best possibly follow and track the multitude of timescales in your environmental context. Of course, music is a perfect example. So now I show you one example, and we are trying really to track these input, and I show you two studies on that, why that is important for consciousness. So here we speak of temporal alignment, which is one of the key mechanisms of the temporal spatial theory of consciousness. We measure basically the brain, how the brain tracks or encodes the input statistics. So here, this is a paradigm in fMRI. It was a self-non-self paradigm, but that's not important. What is important here, it was presented in blocks between 15 and 25 seconds. So, and now what you see in the block paradigm, you can see this here, you see an increase in the power, in the power spectrum in exactly that frequency range. So it's a form of entrainment. You can say it as a form of entrainment. You really see an increase in the power peak. It has been particularly investigated in EEG and the auditory state potential in much faster frequencies, but here you have it even slower. And we have another study where we showed every 50 to 60 seconds we presented two stimuli, and again you see an increase in the power spectrum in that frequency range. So your brain is remarkably adaptive. It's incredible how it tracks the temporal contingencies of your environmental input. Now, we did the same in anesthesia. You don't see that peak anymore. Yeah, meaning in anesthesia, you lose that ability to track the environmental input stochastics. Yeah, you're basically separated, phenomenologically speaking, you're separated from your environmental context. So, and interestingly, the same, that also went along with the loss of the topographic hierarchy. You see here on the upper right, you see the different networks grouped from visual, sensory to DMN, and you see there's an increase there's a clear topographic hierarchy, which is completely lost when you lose consciousness, lower right. So what you have is really a topographic de-differentiation when you lose consciousness, and it's the same for the timescale. The timescales all become the same, they're all similar, they're abnormally long. Yeah, you don't have this fine-grained differentiation, both topographically and dynamically anymore. So that's sort of the concluding slide of this section. What is important, and you will see this, it's timescales, because that's our immediate contact to the world. We see when we look out from this room to the outside world, we look through the windows. Same with the timescale windows of our brain. And interestingly now, I really looked into the literature for the timescales of consciousness. It's relatively short range. It's between 30, 50 milliseconds and maximum 3 to 4, 5 minutes. So the timescale and the timescales of the brain are much larger range. Yeah, we have microseconds, we have nanoseconds. And of course, also the whole day. Your body has also a variety of more timescales, and I need to tell you the world. So that is sort of one key question for us. Why does consciousness have such a small range of timescale? Okay, so I hope I could make a case that timescales are important for consciousness, and we are now also trying more and more also to the experience on the psychological level, the timescales, to measure the timescales there. Next thing is phase dynamics. Phase, you know, it's more spacey, you have the phase fluctuations, and why and how are they important for consciousness. So the hypothesis is maybe they're really important for shaping our contents. And I don't need to tell you, in the visual perception literature, there has been a lot of research on phase dynamics and contents of consciousness. And here we tested that for the thoughts. So here we did a typical attention paradigm. You had to decide response, yes or no, is it a standard or deviant or novel stimulus? And then from time to time, they got these thought probes, meaning was your thought about the task itself, meaning an on-task thought, or were you mind wandering? So it's like either you really listen and pay attention to me, or you just mind wander and think about hopefully the dinner is coming soon, the good Chinese food, which I really appreciate. And the second question, which he said, do you have multiple or single thoughts? You have only one thought, or you have multiple thoughts. And what he measured here was what is called the peak frequency sliding. So this is a method where you basically, this is EEG, so you measure the peak frequency of your amplitude, but the interesting variant of that is done that it is really done based on the phase angle. Yeah, so you have your phase angle and you look what is the peak frequency on that. And then you can control that, whether it's related to the phase angle or the amplitude / the power, through what is called the frequency power, where you basically calculate the modulus of the ongoing phase cycle. So it's not very relevant where the phase cycle is, you just measure the frequency. So, and what he could see, that the phase-based speeds, basically your frequency sliding, really distinguish the on and off thought. So this is in the alpha range, and you can see here the brown ones. These are the on thoughts and single, so you had only one single content and on thoughts, and you see much higher alpha peak frequency than in the multiple thoughts in alpha. Now, then he did the same in the theta frequency band, and you can see exactly the reverse. So now the blue, that's the off-task thought, are higher in their peak frequency than the on-task thought. So given that peak frequency is based on thought, it really suggests that your thought contents, whether you have an off thought or an on thought, is related to the phase cycles in different frequency bands. When you're in an off-task mode, you're probably in a slower, slightly slower frequency mode than if you're in an on-task mode. So then the question is, can we really support this? Because the frequency sliding is indirect. I don't know whether he is here. I cannot see him, Dr. Long. So he, yeah, you want to say something? You want to say something? You present, you did the work, so he did the work, he's in the back. Yeah. So we tested, tested really, it's again a color classification task. You had to classify color and at stimulus onset. He calculated what is called an intertrial phase coherence, meaning the coherence of your phase angles across different trials. Yeah. So if the phase angle is very coherent across different trials, it means there's really an impact of the stimulus. Yeah, of the rhythmically presented stimulus. So this goes back to entrainment. Lakatos, Peter Lakatos, some of you may know him, knew him, yeah, a very, very clever person. So he really showed that. And now the question was, can we link this with on and off and task thought? So in addition to this task, he already did a probe for on and off tasks. So ask the subjects, are you more in an on or off task mode of your thoughts? So, and no surprise, on the behavior level, you see the reaction time. You see the reaction time for on thoughts. It was shorter because if your thoughts are on the task, of course you react faster. So meaning your thought mode on task or off task thought really have an impact on your behavior. So Now, this is the intertrial phase coherence. And what you can see, I just focus your attention here on this one, on the on-task, and here on the on-task again. You see the yellow peak, that's basically the degree of ITPC. You see it here in the theta range. It's stronger, and I show you the figure in the next one. This is significantly stronger than when you're in an off-task mode. So I show you the findings here. Here you see the upper left, you see the black and the red curves. That's basically your on-task mode, and the other curves are your off mode. So meaning when you are in an off mode, so you think about something else, your phase coherence is much less than when you really focus on the task. So meaning there might really be that the phase contents impact, exert their impact on your task performance through the phase coherence. And that also correlated with the reaction time. So meaning if you had less phase coherence, you had longer reaction time, which makes sense. So meaning that how one way of the thoughts exerting their impact on your cognition is through the phase cycles. And as I said, we have another paper in revision where we again show this in a different way. And Dr. Long has another wonderful paper in the loop for that. So it really seems to be that your contents, your thought contents are shaped by the phase. So by the phase cycles. So this is for me as a psychiatrist very interesting, because what I see in schizophrenia, I see a formal thought disorder. Yeah? And we show in schizophrenia that the phase cycles are very imprecise. Yeah, and so here it's a summary figure. Basically, when you're this is your external cognition. This is an easy task. This is a difficult task. I left out here the modulation of the phase coherence by the difficulty of the task. But what you can really see, these are the phase angles. You have a high intertrial phase coherence. When you have on thoughts, you have a low intertrial coherence when you're in the off-task mode. So meaning when you're in an off-task mode, you're not as temporally precise anymore. Things become more blurred. Yeah? And that's probably also on the phenomenological level of your contents. So the question is now you say, so now we're really trying to establish what we call thought dynamics. Yeah? Because usually thoughts are only approached in terms of contents, but maybe there's a thought dynamics. And as I said, there's more papers coming out from our side that we really show differential thoughts, differential neural phase, particular phase dynamics. So if that happens on the neuronal level, you would expect maybe there's also a dynamics of thought on the psychological level. So you see, I always try to go neuronal psychological level. So this is a study which we did, and now we're continuing doing this paradigm. So here it's just a psychological study. So what we asked the subject to be aware whether they have more internally oriented thoughts about their own self or more externally oriented thought about the external environment. So, and that we did and then because we had a good number of trials, we could calculate a power spectrum. So we have a number of trials, internal, external thought changes, and also the degree of awareness. And that gives us the possibility that pure with behavioral data, we can calculate a power spectrum. So a power spectrum of your thought, internal, external thought changes. Trust me, we worked very long on this, but now we're doing this more and more. So, and this is, for instance, one result from that, this is a healthy subject. You can see very nicely, you have different frequencies. This is basically your internal, external thought change, and the power on the y-axis is like a power spectrum, yeah? On the y-axis, you see the power. On the x-axis, you see the frequency, and you see the thought change. And now we did this in depressed and in bipolar depressed patients. So because it's a clinical application here. So now look at the depressed patients. They don't have much thought change, they have a slower frequency and not much power. And that's exactly what they experience. Now I give you some of the more quantitative data. So now you can really investigate just the power. Like what you do in the EEG, you calculate a global power, and that's exactly what we can do. I know it sounds a little strange. We discussed it a lot with our engineers who are the expert, and you have to downsample the data. It's not an easy one with the sampling rate and everything. So now we said, okay, this is a power of your thought changes. And as expected in MDD and bipolar BD depression, you really see a slower power. And again, that's exactly what they experience. They experience a lot of thoughts, yeah, but completely no power, no energy. And that's what a power spectrum is ultimately. So then we looked for the frequency of thought changes, and you can see that particularly in MDD, you see the significantly slower frequency, but not in bipolar. So there might be a possible differential diagnostic instrument here, which is clinically very important. So what you can see, and that's exactly nothing changes. Everything remains the same. So that's why we coined the paper Slow and Powerless Thought Dynamics. So then we also did a mediation model. So we found at least a partial mediation between the power spectral density, and this is brooding as a subset of ruminations, is circulating thoughts, and your depression severity. So what is important here, that the thought dynamics is the independent variable. The classical model would have expected that your depression severity, back depression inventory, is the independent variable. That the thought dynamics is a consequence of your depression severity. But that's not true. It's the other way. We have various models supporting this kind of structure. So I hope with that I could show you phase dynamics is important in structuring our thought content and possibly also our conscious content. The kind of contents you have, like remember, off or on task thought, which you, and this would be nice. Similar I expect, of course, I expect for other modality, for affective consciousness, for perceptual consciousness, and so forth. So I'm coming to the end, wrapping up. Temporal spatial theory of consciousness. I hope I could make clear what I mean by common currency. So very simple, you share something. Yeah, these different European countries share the currency. Yeah, and same I said, okay, there are a lot of differences, but they share the currency, the euro, and that makes communication easier. Same on the neuronal mental level. We say there are different features. I acknowledge neuronal mental states are not the same, but they share something, and that makes a connection. That's what I mean by time and space. Here, this is a figure from where we showed various examples of a common currency, meaning similar measures. This is a very recent paper this year. Neural fluctuation, you see similar attention fluctuation. Alpha theta frequency, the on-off start thought I showed you. And here it's also from the depression that we see functional connectivity is literally delayed, global to motor cortex, and you see a similar psychomotor retardation. So temporal structure on the brain translates into mental temporal structure. Same on the spatial side. Remember the unimodal transmodal gradient. And the balances between these different gradients is basically your inner-outer cognition. You remember that figure with depression, mania, and meditation. So now, of course, the key question you would ask, yeah, Northoff, all nice and dandy, but how are neuronal and mental activity related? Yeah, even with the similarity, you still need to say, what is the relationship? And that's what we assume. It's a correspondence, again, in this paper, but it's not a one-to-one correspondence. Let's say, for instance, the longer time scale in the brain can still be related to a shorter time scale in the mental side. Why? Because you have a discrepancy in the time scale range between brain and consciousness. That's my background assumption here. Various example for details, I refer to that paper. So that's what we developed. This is the common currency is really one key feature of the temporal spatial theory of consciousness. And we introduced it in 2017, and we're working on an update 2.0 for next year. As we changed, it really developed. So, and now you say, I come to some application and then I finish my talk. So why do you say it's relevant? So now we also try to apply this spatial temporal principle for therapeutic interventions in mental disorders and mental being. So, and one of the key features of depression and also anxiety is that the speed of the brain is either too slow, as in depression, or too irregular in anxiety. So there's too much high entropy in both neuronal and subjective mental activity in anxiety. So the question is, how can you provide a therapeutic tool? So what we are doing here is that we do the breathing. Now, when you look online, you say the standard slow breathing protocol is 6 breaths per minute. However, we say, because we see so much differences between different subjects, we say maybe we want to basically test which breathing rate is the best for the individual subject. So meaning we are trying really what is called precision psychiatry or personalized psychiatry. So what we do, subjects come, get an EEG, and doing the EEG, they test different breathing rates, 4, 5, 6, 7, 8, 9, and 10, and for 3 minutes. And then they need to fill out little visual analog scales about their level of anxiety and their thought racing. Yeah, that's what you saw here. No. So, and what we see, the first thing is, that is on the psychological level quite interesting, that with increasing breathing speed, you have higher anxiety and higher thought racing. Meaning the faster you breathe, the higher the likelihood that you get anxiety. So this sounds trivial to you, but when you look into the literature, it hasn't been shown. So there is a speed dependence of your anxiety and your thought. We do the same. I show you more data with music. So now what about the therapeutic effects? They're quite dramatic. So the subjects get an up with their personalized breathing rate, and most of the subjects did not like 6, they had 4, 5, 7, or 8 as preferred. So, and then they get this up with their personalized breathing rate, do 10 minutes of breathing in the morning, 10 minutes of breathing in the evening. So, and that's what I show you here. And before and after these 10-minute sessions, they have to do again these 2 little visual analog scales. And what you see, it's again quite a dramatic reduction in your level of anxiety and thought speed after 10 minutes of breathing. Yeah, and you see, important, it almost holds about 90% of all sessions. That's really important because then the patient knows, aha, if I do the breathing, it will help me. This is much better than taking any benzodiazepine or other things. For instance, I have one patient. She's an engineer. She's absolutely brilliant, suffered from social anxiety. And I told her, she came to us, and I told her, how about doing the breathing before you give the talk? You go briefly to the restroom, do your breathing for 5 minutes, and then you go out to the talk. It really helped her. So this 10 minutes immediate effect is huge. You don't see that usually, particularly the 90%. Then the 3 weeks effects, also very good. You see the effect. This is a back anxiety inventory. You see a very good reduction over 3 and 6 weeks, T2 and T3. So, one more example, and then I close. Personalized music. So we all music. So here we test same thing, speed of music, and we personalize. Original versus preferred speed of music. And here again, the conceptual background idea, speed is important for your mental features. As I said, we have a whole line of research where we really show depression is a speed disorder. It's not just a mood disorder, it's a speed disorder. Yeah? And what do music and brain share? Time scale. That's probably why we are so responsive to the music. And here we do the same thing. So the subjects bring 6 preferred pieces, and then we let them, then we manipulate the speed of those pieces, 3 slower, 3 faster. And then they listen to all 7 speeds, And again, they have to fill these little visual analog scales. In addition to thought and anxiety, they also have to be about happiness, agitation, and movement, how much you want to synchronize. So, and then again we did, and amazingly, 90% of the subjects do not like best the original speed, though it's their preferred pieces. So you bring a piece, let's say the Beatles' Yellow Submarine, and I manipulate the speed, and that's your favorite piece, and then it comes out that you maybe like a slower version better than the original. So you know this piece in and out. You can't imagine how surprised we were when we had this. And it's replicable, which is even for healthy subjects. So meaning speed matters, yeah, and the speed of your brain is highly individualized, yeah. And here again, the speed dependence. This is for me the fascinating thing, the speed dependence of your emotions. If you become faster, you show higher anxiety, higher thought racing, yeah. So if I really want to make you anxious, I speak super fast now, yeah. And now we're trying also to get into the neuronal side and showing that. So now the immediate effects, again, you see the immediate effects here. Blue is before, and 10 minutes is the same thing, 10 minutes in the morning, 10 minutes in the evening, with the preferred speed of the music piece. Now, this is an individual subject, which I find very impressive. So the blue is again before, and the red, the orange, is after the 10 minutes. And each of these is 1 day. So this is 72 days or 71 days, the level of anxiety, how much each level. And this is not an exception. I do not just show you here the sherries. Yeah, I really show you, this is really the data. It's quite amazing. And the same thing then after 6 weeks, this is the anxiety sensitivity index. You see quite a good reduction. So this is a tool which can not only be used clinically, but for mental health intervention in general. That's sort of the idea. And now we're trying to run this also with younger people, because I don't know how to see in China, but in Canada, we have a huge increase of depression and anxiety among young people. Very sad to see. So my hope is that we can help them without getting them into this maze of psychiatric treatment and pharmacological treatment, yeah, which can ultimately not so beneficial. So yeah, with that I come to the end, and I hope I could show you that maybe consciousness, we don't need to invoke any complex property like integrated information. Of course, the Tononi theory has certain truths. I think it's a brilliant idea and brilliant aspects in this theory. But I think we really need to go to the basics. And what I said, it's maybe not a special feature, it's the most unspecial feature in our brain. Thank you very much.